Hello, welcome to another episode of Xan Talk Show. So we are going to code Wolfram language doing a animation of physics simulation of bouncing balls. My keyboards, Glove 80, fantastic. Nulia trackball, fantastic. Logitech 405 mouse, fantastic. Something like 405 or something, 406. And Ultimate Hacking keyboard, okay? And then there is this Swarboard, fantastic. Okay, I'm gonna try to use it. Okay, watch my videos. For each one of them, I have a video on YouTube. Okay, so let's stop that. Let's start to code Wolfram language. Let me show you what we gonna do. If you are watching offline, play at 1.5 speed because I ramble. Now there is this fantastic animation. Okay, let me show you this animation. Okay, let's go to it. We're gonna code this. Let's see, we need to turn on sound. Start again. Fantastic. Okay, we're gonna code that. I've never done this before, so I'm just gonna see how we are going to explore how to do it with Wolfram language. Meanwhile, I'm gonna show you how about Wolfram language graphics programming. So if you are new to Wolfram language, I have like 100 videos in the past, and about 2 weeks ago, we had this one about how to introduction to Wolfram language programming graphics. Okay, so watch that one if you don't know yet. And Wolfram language, so I got search for Wolfram language tutorial xali.info, and you can download it for free over here. And you can download Jupyter extension, and there's another one that allows you to have interactive graphics without buying it. Okay, download free. And okay, so let's just code it. Okay, so this is today's talk show. Yeah, so in order to do animation, there are like the most basic way is via geometry. So that is, if you want to do an animation, all you need to know is, let's say we are limiting ourselves to 2D geometry, but this works in 3D geometry or live action or movie, anything. So all you have to know is the graphics for each frame. Okay, now but in 2D geometry, or such as this thing, all you need to know is the if you are here, say hi. Okay, if you are watching live, say hi. Love to see your comments. Now if you are doing animation for 2D geometry, all you have to know is that each object's position with respect to time. So if you have an animation of, let's say, 1 minute, so each second, position, you need to know the position of each object. Then just draw it. Then you can create the whole frame, and frame by frame, it creates animation. So in summary, you need to know the most basic ways to know the position of each geometric object. Okay, that's how you do any animation. You can do any animation. Now, that's the most fundamental basic way. Now, a more higher level way is that you, let's see if I have written it out. Yeah, so I have, so one way to create animation is to know position of each object in any frame, okay? Now, a higher level is to create animation is to know an object's begin and end position and specify a rule to determine their intermediate positions, okay? So instead of drawing each position in each frame, you just say the start position, end position, and you give it a function, how it will go through time. So as time increases, the function will specify the position. So that's kind of higher level. A more higher level way is actually to do something like this, is actually you write a physics emulation. So that is getting more complex, but which is in many game engines, they do that. So what you have to do is you specify the rules. I'm not familiar with this, so but I think basically you specify the physics rules, the ball will bounce and stuff. And so all you have to do to create animation is to specify your object and initial velocity. So the direction and speed it's moving. That's all you have to do. Then you just run it, and as the object moves, it will the physics engine will detect which position is that, what direction it's going, if there's an obstacle. If so, it will bounce it back. It will move the object in a different position according to the physics engine's rules. Okay, so in this framework, all you have to do is specify object and initial velocity. That's it. So, but we are going to do, so I never done this animation like this. This, looks like a physics animation, so I never done so. But we're gonna do this, okay? So it turns out it's easy. You can do it in a most fundamental geometric way, because you observe, first of all, in order to do this, first of all, what you need to know is what exactly it is doing. In physics terms, you just, it's just ball bouncing. But in geometry, you observe the first ball, so you can determine basically the balls, their path is always the same. So the top ball always move in the same path. It never falls down. So it's not actually physics emulation. It just go back and forth. So for every ball, they traverse in the same exact path. Then you can know that by just watching, focus on the first ball, the dark red. And then you can observe the last ball. You can also see their position. The path is always the same. Okay, that's the position of each ball. The other thing you determine is do they have different speed? That's one question. The other question is do the speed change? So you can observe each ball in the animation. Then the top ball will have faster speed than the last ball, because when you look at the first frame, you see the first ball traverses all the way back here, while the last ball is much slower. So the higher the ball, the speed is faster. So that answers one question. That is, each ball have different speed. Okay. Now the second question, does the speed change? If you watch the video, you'll see that the speed does not change. So each ball have one speed, and they don't change, and they traverse the same path. Okay, so this whole thing becomes very simple. It's just geometry. Each ball traverses the same path. The first ball has higher speed than the last, and the speed never changes for each ball. Okay, so that's all you need to know. So once you know that, I've written out, because I written out. So once you know that, then you can determine each frame's object position, and you can create the animation. So we're gonna do that. I posted this yesterday, and someone it's fascinating, and someone asked, do this in Wolfram language. And I was like, I don't know how to do that. So, because this kind of physics emulation I've never done, so I thought about it, then it turns out pretty simple. So let's begin. Okay, so let's begin. Let me try to do like kind of as fast as I can, so that so we start a Wolfram language code, because this might take an hour because I never done this before. Okay, starting Wolfram language. Comments, any comments? Nobody, okay. So Wolfram language, let's start it. Okay, so let's say 3, 2, evaluate, shift enter to start a kernel and magnify so it's easier to see. Okay, so we got, okay, now let's save it. Save it. Animation, just random name, okay? Okay, so we start to code. So we're gonna write the animation to do this. Hold on a second, let me see. Can you guys see it? Okay, so we want to, yeah, so we want to, okay. Okay, so let's begin, okay. So we, okay, let's just start, okay. Ball, so ball is a graphics primitive, okay, so do I have, okay, look up the ball documentation. Ball is a function that represents a disk. Okay, so we want okay, we don't want ball. We want disk, which represent like a ball. Okay, so this radius. Okay, so let's say 0 position at 0 0 radius 1. Okay, now we want to show this in graphics, so you have to do is put the disk inside. Okay, then run it, you can see a disk. Okay, then we can say axis true. Okay, so actually then we need to plot range. Plot range, let's say -1 to 1 times 10, then same for y-axis. Okay, so copy that, let's do this. Okay, so copy that. Okay, we got kind of ball. So range, let's increase to 20, 30. Okay, so we got a disk, so that's one ball. Okay, so that's one ball. So now we do, so I'm coding this in Emacs using Wolfram mod. You can download it. It's linked on my talk show. You can download it, Wolfram mod, okay, on GitHub. So I do this in Emacs because for me it's easier to code. You can directly code in the Wolfram notebook or Jupyter if you want. So we got this. So now we just got a static graphics. Now we want to move. Okay, so let's do a move. Okay. Manipulate, let's look at the documentation. I kind of already know what that does. So manipulate, I mean, takes an expression and takes a range. So this is gonna be time, let's say x time from 0 to, let's say 0 to 1, okay? So then in this, the expression with variable x time will change, okay? So now let's say, let's put the graphics in here. Let's see. Okay. Let's say animation equals to that, okay? Then you need a time thing, okay? So wait. Okay, so this animation, you need a time. So the time will be the position, okay? So let's change the x-axis, okay? Time there. So that's the animation. Then you okay, so let's just do that. Let's see if that works. So 0 to 1, instead of 0 to 1, let's say 0 to 10. Let's say negative 10 to 10. Okay, copy that. Paste, run it. Okay, got a problem. Because, so time negative 10 to 10, this needs to evaluate, I think. Okay, there we have it. So let's, so can you, you need to drag it. Okay, so you can see we got animation. You can back and forth, okay? Fantastic. Now, this ball, we have to draw several balls, okay? So we got the animation of one ball. Of course, we need to color it. But why is it no autoplay? Usually there's a play. Okay, so oh yeah, okay, so you click on that and say back and forth. Okay, then we got a ball. So we need to change the ball path. Then we need to draw two kind of bars, okay? So, okay, so I need to think about it because, so you need, so this, you know, so, okay, let me just, you know, like keep typing. That's a key for live coding because, you know, don't think, okay, let's just keep typing. So graphics disk, that thing, and so this time is gonna be a parabola, okay? So it's gonna be a parabola. So parabola, the curve for a parabola is just x squared, okay? For example, you can plot that. You know, so if you go negative 1 to 1, let's say negative 9 to 9, shift enter, there you go. Okay, but now it wants an inverted parabola. So this is basic analytic geometry, pre-calculus analytic geometry. You learn this before you do calculus. So you want to invert the axis, so it's just negative, okay? So okay, you got something like that. And then, okay, so this is the path for this, the position of the ball will be, let's say, the position of the ball will be the parameter formula, okay, so which is, let's write it out here. So it's a parametric equation of two things, x and x and 2. Okay, so so instead of using x time, let's just say x. It's simpler. Okay, so time is just x. Okay, so so now, okay, so now this, you got a parabola there, and yeah, so x is let's change x to time actually. Okay, because it's easier to see. So you got let's just do it. Okay, keep typing. Keep typing is a key for live stream. Okay, you got a problem. Oh yeah, you forgot to evaluate. So manipulate, you need to evaluate. Okay, evaluate. Add is a shortcut for the square bracket. Okay, it's a prefix notation. Copy that, paste, run it. Now how do I play? Expand, play. Okay, there we have it. Okay, so the parabola, right, you invert it. You invert the parabola. Okay, now we can do something. You can see. Now, what is 10 squared? 10 squared is 100. So it actually went all the way to 100. So let's stop that. Let's change it to 0, 1, 2. Let's say change to 2, 2, 2. Okay. Play back and forth. Okay, so you kind of see where it's going. Okay, then let's shrink the range. Okay, now 2, 2, 2 and shrink the range. 2, 2, 2 is 4. Let's say 4. The plot range is 4, and the time is from -2 to 2. Okay, copy that. Let's do it here. Right. Oh, now the ball is fucking huge. Okay. We got the ball going, something like that. Okay. Now, okay, stop that. Stop that. Delete that. Okay. Delete that. Okay. Now the ball is too big, of course. Now the radius will be 0.2, let's say. Okay. And the plot range is going to be, the y-axis is going to be -4 to 0. Okay, let's say 0.5. So that will be much better. So let's try it. Paste, run it. Something like that. Okay, so that's one ball. Okay, next we can add a color. Okay, so color, so all you have to do is add a color, hue. Okay, hue 0, that's a rainbow color. 0 is red. Okay, so we got a ball. Now we need several other balls. Okay, so let's add them. So we create a list. So this is one ball. Let's put another ball here. Okay, so copy. Now hue this one, let's say 0.3. Okay, 0.3 0.4 is blue. Okay, 0.4 is blue. Hue 0.4. So and this, but the path for the second ball, if you look at the animation. Okay, can we show the animation here? Okay. So the path. Okay, so it's actually red to blue. The rainbow. It's not the whole rainbow color. It's like 1/3 of the rainbow color. Let's make our whole rainbow color. Okay. So that each ball is very distinct color. Okay. So, but the second ball, yeah, you see, if you observe you see, you look at the second ball, like this one, okay? Look at their path. It's a bit lower, so basically a bit lower. So how do you make the parabola lower? That's a basic analytic geometry. So you got the parametric curve, lower just y-axis minus, okay? So you just minus, let's try 0.2, okay? So let's see if that works. Exploratory programming, okay? We got an error, comma, error. Shift enter again. Okay, we got two balls. Okay, we got green instead. Blue is 0.6. Okay, so there they go. So they actually, they actually have exactly the same path, but one is lower than the other. Okay, and increase the speed. Doo-doo, 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 doo-doo. Fantastic. Okay, now you see. Now one of them, this is gonna get a bit complicated. So this ball, let's just say red. Okay, let's just not fuck with the color. Let's say blue. Okay, easier to read. So red ball, blue ball. Now blue ball needs a slightly lower. Okay, and the path needs to be smaller. Okay, because so you will need to so you see the time is a parameter, so t goes from -2 to 2. Now for the blue ball, the range must be smaller. Okay, so how do you do that? The range must be smaller. You can manually code it by you see the time varies, so you cannot just minus something. You need multiply. Okay, so again, this is fundamental of like calculus. Like, that's the first thing you really need to master about how the parametric equation affect the graph. So you can time 0.9, okay? So that time 0.9, okay, 0.9. And this part, same thing, okay? So let's put the negative outside, okay? Let's try it. Exploratory graphics coding. Do it. Okay, we got red and blue. Let's see. Play it. Back and forth, back and forth. Increase time. Doo-doo, 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 doo-doo. Fantastic. Okay. Now, next we need to... Hello? Anyone here? Angan says, "Hi, I don't know much about physics and math yet. Got recommended this. Could you tell me what Wolfram is and why are you doing it?" Okay, we're doing it to show programming. It's a fun programming task, and it's doing animation, graphics. So it's about graphics programming. So if you are a student learning calculus or mathematics or programming graphics, or you are an engineer, or if you are a professional scientist, you want to learn something about Wolfram language, you heard about it, you never used it, this is the video to watch, okay? And I explained many times in my past videos, Sound Talk Show. So there's an entire Wolfram language tutorial. Where do you download it? And entire graphics tutorial. I've done like 100 videos on Wolfram language. Okay. Okay, so back to this. So yeah, did we try this? Successful, fantastic. Juju, juju, juju. Now we need to connect the line between the balls. Okay, and actually we can play a sound, but yes, we can. Well, yeah, you can. So anyway, so connect the line. That's easy. So you need a line. Wait. Okay, so you need the line. Line takes a list of points, so 1 point, 2 point, or 3 points or more. Okay, so let's add another ball actually. 红橙蓝绿. Okay, now this one is green. Okay, green ball. Let's say this one 8. Okay, 0.8 and this 0.6. Okay. 3 balls. Now you need a line connecting the 3 dots. Okay, oh god. So this, you need to copy that. That's the position of that one, then position of the second one, then position of the third one. Okay, so after you done this, you can clean up the code so that you don't have to like repeat all these. Okay. Okay, that's a line. Now double check you got it right. Yeah, so you got the line. Yes, and make the whole thing a bracket. Okay, so once you have a bracket, you can add colors and stuff. Okay, but let's just try that. Okay, fantastic. Are we good? Increase speed. Okay, something is not correct. Wait. Okay, you forgot to lower them. You see the green ball is too high. So you need to, you forgot to lower them. Yeah, so the green ball is, let's say 0.3, 0.6. So back to Wolfram language here. Paste. Now Control Shift N to typeset it. Now it's beautiful. Now you see the typeset automatically formats on the fly. It's much better than Python or Haskell or C or C++. This technology has been around in Wolfram language since 1996. So you never need to worry about tabs and space. You see, there's no tab here, no indentation. But the Wolfram language, you see, automatically does it for you. And on the fly, depending, so as you type, it automatically formats. So all the, industrial coders, the Python, Java, Golang, Haskell, they are all crap. They need to have this feature, okay? Automatic formatting on the fly. So I talked about this in many videos, in past videos. Search for it. The last one is like 3 months ago. Search for, the Unix line truncation. You'll find it, my YouTube. Okay. So anyway, so we got this. So Shift Enter to run it. Okay, we got this animation. Let's play it. Play it back and forth. Increase speed. Okay. Okay. Now you forgot to. You see, you changed the formula here, so you forgot to, so actually paste do it. Okay, play back and forth faster. Okay, now the balls needs to be lower a lot. Okay, I think we got our formula wrong. The green ball, look at the green ball, they need to be much lower, so there is something wrong in our formula. Okay, oh wait, so the formula starts to get complicated. Oh yeah, you forgot. So wait, you inverted. You see, we inverted. Oh, okay. So the negative needs to apply to the whole. So you got, yeah. So yeah. Okay, and you need to do the same here. Copy back here, paste, run it. Now it looks better. Now it looks good. Back and forth, increase speed, play. Okay, that's wrong. Okay, but similar. Okay, so you know, so but it's not correct. Well, the reason is because we need to diddle with this parabola. So let's think about it. Okay, so you shouldn't apply the whole. So you invert it by applying a negative, then you need to move it down. So you invert, so parabola is like that, you invert it like that, then you move it down just minus, right? So why is our code not correct? Did we forget something? You know, why is our code not correct? Oh, then now you forgot the line. Oh yeah, for you see, did you? And now it's like the line is not connected. So instead of this, you know, now it's getting complicated. You should write a formula so you don't have to repeat this. So, but so disk of size 2, 0.2 radius, and this formula is that. So what is so you negative in wait, you negative the y-axis, you invert it, then you move down, right? Minus 0.3. But the line is not connected. Why? So the okay, so make sure we got this correct. Yeah, needs to be exact copy. Okay, yeah, so we missed, that's why the green ball is like not connected. But how are they different? 0.4 squared minus 0.4. Wait, how is it different? Why is it not? Oh yeah, so you forgot to remove that. Yeah, let's try it. Play, back and forth, increase. Okay, so you need to be much lower. Okay, so but essentially we effectively did this. Okay, so 0.3 is going to be 1, let's say. Okay, 0.6 is going to be 2. Wait. Okay. We need to figure out, so you got several balls and each one, their position differs slightly. So you need to write a formula so that you don't have to like hard code each one. You can just, so it's systematic, 0.8, 0.6, 0.4, but the basics is like this. Okay, so actually you need to now it's more like it, you see. Okay, so then you need to change the range. The range will be different for each ball. That is the range, that is the the time, this 08, 06, that changes this range. And you need to do some geometry to figure out, so given a curve, parabola x squared, minus x squared and plus or minus some constant, you need to figure out when do they all align on the kind of like a V-shaped axis. Once you know that, the initial time parameter for the parabola, then that's how how they relate to 2. So you want to make this -2 plus or times or minus something, so that for each one of them, they will all start at the at that. So that is that part is mathematics. You can figure it out. You need to do some plot. You can experimentally figure it out how the initial position is. How do you make the initial position align on a bar, on a diagonal bar? Or you can solve this by mathematically figure out, the square root. Yeah, you can actually square root equals to a number on the x-axis and y-axis. Okay, yeah, you can figure that out by solving an equation. Very, the most simple. But basically, we got this done. Basically, so we got this. We can now actually make a sound. How do we play the sound? Okay, adding the sound would be a bit more difficult, because right now, okay, so actually we got a problem. This is not correct, because the framework so far is not correct, because the way we are doing it, all the balls are just going back and forth. They never become out of synchronization. So you need to make them out of synchronization. Okay, so in that case, you need to start to use sine and cosine, because sine and cosine, that's how, we need to do that. Hey, Hank. So we're coding this animation. So, you can look at my website, Xar Talk Show today, on the link at the description. You can check out what we're doing. So now we need to make this go back and forth. Okay, then that is okay. Let me try to get that. Then that's it. Then that's basically it. So we need to get the ball. So right now the ball all sync. Okay, that's not what we want. We need to get the ball out of the sync. So in other words, the cycle is not just the beginning and end, you see, of the time range parameter. So in order to do that, you need to, so between -2 and 2, you need to start to get sine and cosine, because sine is the function to repeat in mathematics, okay? When you want a function to repeat, basically sine is the function. Well, sine is a smooth function. I mean, you could also define a function such that, during 0 and 1, it's 1. From 1 to 2, it's -1, things like that. But then it's not continuous stuff. So usually sine is the best thing in math to get a cycle, okay? So you want let's just focus on one ball, okay? On one ball. You want it to repeat this path. So what you want is a parametric formula, like this one, for x and y, such that doesn't matter where x is the input, the output is always back and forth, okay? So you want a function such that, let's say x goes from 0 to 10. But however, your functions x will become from 0 to 1 and back to 0, 0 to 1, back to 0, and so on, okay? So you can do that by sine. That's right. Again, let's just keep typing, okay? Let's just keep typing and we'll see. So you can, then you're gonna have lots of fancy graphics, okay? So we got a sine. Let's just say that it's gonna be like wild. Okay, back here, paste, evaluate, okay, show back and forth, increase speed. So you see, do they get out of sync? Okay, so I don't know. Okay, yeah, in order for sine to work, the parameter needs to increase, because sine, the period of sine is 2 pi. So the parameter needs to be like 20 pi. Okay, so something like that. We can check out what's going on. Okay, something happened. Increase. Okay, they went, yeah, so I know. So now let's keep doing. Okay, before we do that, let's have a backup. Actually, let's have a previous version saved before we did the sine, okay? So this is before we do any sine, okay? So okay, this is all the balls are in sync from beginning time param to end of time param, okay? That's this version. Now we're gonna start to have them to be out of sync. So this will be wait, so this needs, okay, so this needs to be copy, this needs to be inside, this needs to be inside. Okay, now we change all the parameters. Okay, so again, okay, so copy, paste, copy, paste. Okay, now yep, now let's try copy, oh, and wait, let's just run it. Wait, stop, all the way to the bottom, run this. Wait, did we do it? Wait, this there's no sign. Okay, no, not that one. So copy, paste, run it. Okay, this is the new version. Play, back and forth, increase. Okay, so they don't. Wait, so this is not correct. We are not seeing the effect of sign. The effect of sign should at least have 2 cycles, so you should go back. You see, if we play it just forward, it should automatically come back. Yeah, because we put the sign there. But why is it not doing that? Let's see, sign. Let's make it all positive. Okay, so sign becomes positive and negative, positive and negative. We want the x-axis to be always positive. Yeah, so okay. Wait, did we get the error somewhere here? What? Paste, okay. Do it. Now run this. There it is. You see, it started to shrink back. Okay. So now all you have to do, yeah, so the x-axis, you see, I see now it's limited. You see, sign output is always less than 1. -1, +1. Okay, it cycles in between. So you need to increase that to 2. Okay, so God. Okay, it's becoming more complex. But we're getting closer. Yeah. Run it. Play. Okay. Then we need to, so let's say 4. Now we got too many. Hold on a second. Copy, paste, run it. Okay, why is that 4 pi to 2 pi? Oh, it's not cycling. Output 2. Okay, so so far so good. Okay, so so the input, the time, negative 4 pi times 2 pi to 4 pi times 2 pi. So the input is, a huge range. 2 pi is like 6 times 4 is like 24. Okay, so we can change that to 24. 24, negative 24 to 24, that's the time. So when negative 24 times sine, it always becomes negative 1 to 1, then you absolute, it's always 0 to 1. It needs to be negative 2. So because parabola, you want to, it needs to be negative, so not absolute. So delete that. Okay, so that would be better. So you need to go between, okay, between negative 2 to 2. Okay, so that's the output for x-axis. X-axis, negative 2 to 2. Cycle them. Okay, the y-axis don't cycle. Okay, now this should do. Wait, paste, evaluate it, run it. Okay, it's not coming back. You see, this just one shot fast. Now let's you need to adjust the plot range. Plot range negative 4 to 4. X-axis, y-axis is negative, let's say 10. Y-axis negative 10 to 1. Okay, to 0.5. Okay. Let's say 0. Okay, shift enter, play. Where did they go? Okay, plot range, it disappears to the let's look at this one. Okay, we are not seeing cycling. Okay, why is that? So you go through, this is like (24), let's say 30. Okay, so this is like 30 to 30. Okay, and then sine time, sine time is always negative 1 to 1. So it will go back and forth, negative 1 to 1. Then you multiply by 2. You multiply so it's less than 1, you actually shrink it. So you want, instead of divided by 2, so this is negative 1 to 1. Let's just say 0 to 1. You times 2. Times 2. Times 2 is right. Okay. So you get that. So, but why is that? So plot range, let's say plot range 10. Let's say plot range 20. Copy. paste, evaluate it. What is this? Hide controls, play. There you go. So it's kind of fascinating. Now I'm not sure why. Okay, so it is doing a cycle, but it is not doing the right cycle. You see, it is doing a wait, it's not doing a cycle. So there is something we did wrong. Okay, we already coded for 1 hour. I think maybe we should stop. So what is wrong? So do we need to change the y-axis, the function for y? No. Wait, let's look at the x-axis. So you see, if you look at the position of the balls, their x-axis position, it's always within 2 and 2, you see, right? So now we can, if we change 2 to 3, then we got a wider thing, okay? 2 to 3. Okay, so then you get wider. Now what about the y-axis? The y-axis, why are they going up down so much? Let's observe. Let's look at the red ball, okay? Let's stop. So you go move, you go, so when it's, oh, I see. You see, the y-axis, they become huge. When you range over a large number, the y becomes very large. That's why they disappear at the bottom. So you need to clamp them. So what you do is you can, so again, basic analytic geometry. So you need to clamp them by how much? 30 squared is 300. Okay, 30 squared is 300. You want to limit it to between 0 and let's say 10. So you need to so you need to let's say what range we want, 10. Okay, so 2 times 2 is 4, 3 times 3 is 9. So let's say limit it to 9. We want the y range to be within 9. Okay, so this part should be within 9. Okay, so but you are ranging over to 30, so 30 times the number equals to 9, so that means 9 divided by 30. So okay, so you want to time 9 divided by 30, something like that. Which is 3 over 10, okay? But okay, but let's do it. So okay, then so this is, you need to do that before you move. Okay, so that before you move them. That's right. So there, there, there. Okay, let's add a space. Copy. Now let's see. Fantastic. Play. Wow. Okay, stop. Now look at the red ball. The red ball is doing some kind of figure 8 curve. The red ball is going, so if you look at the red ball, the x-axis is within 2 and 2, okay? It's within 3 and 3. But if you look at the y-axis, it's going all the way to 20. So this is not right. If you look, so let's see, look at the y-axis. Look at the red ball y-axis. So it's going up and down. It's going up and down in one cycle. It's going up and going down one cycle. So something wrong with the y, the part for the function for the y. Okay, we don't want that. So why is that going all the way? So it becomes 20. So 30 squared is 300. Okay, so 30 squared is 300. So actually, okay, let's fix. The part range x is 323. So let's make x width equals to 3. Okay, let's make it easier to understand. 3 3 3 3 3 3. Okay, that's the width of x. Now and so it's becoming more complicated. So y x squared so let's say time range equals to, let's say 30. Okay, 20. Okay, so then we got X range, time range. Okay, then you got X range, time range, so Y width, what about Y width? Y height, Y girth, Y height. Let's say Y width. Okay, Y width should be just 9. Okay, -9. So if you want to rename, so why is it Y going up? You need to think about this. X is traversing. X is X max. Okay, so let's use a better name. Okay. Okay, so X max, time max, X max, then Y max. So now Y max, what should Y max be? So now Y max should be time max squared divided by we want let's say 5. Let's just say 5. Okay, we want it to be 5. So we don't want it to go below 5. Okay, then so if you don't want it to go below 5, then the value should be dynamic. It should be max squared times something equals to 5. 5 divided by, that should be something like that. Okay, Y max divided by X time max squared. Yeah, so something like that. Okay, so this would be 5. Okay, so now you're getting elaborate. Since you are defining variables, you need to kind of clean them. You see, we use a double colon equal, so that means it's computed dynamically, okay, not just static. You see here, this double colon equal, that means it's computed dynamically. Okay, so now Y max needs to be this. Okay, now it's much simpler. Is it good? It should be all good. Okay, now copy that, and it's, please make it work, please. Oh god, error. What error? Check coordinate something cell context y should be a pair. Okay, we got some kind of syntax error. Okay, that's the error message there. Coordinate something cell context y. Okay, so oh wait, this is wrong. This should be 5. Yeah. Copy. Paste. Run it. Fantastic. Let's see. Whoo-hoo! Now we talking. You see, thinking does the work. You always need to think. You cannot just like trial and error. Okay, so now we need to adjust the plot range because we don't need the whole thing blank under. So you see, because we made sure it's just 5. You see, that's magic number. So let's define it. Something like that. Equals to 5. So you got one more variable, y max height. Okay, so y max height equals to 5. Then you just, the plot range is just negative y max height, and the plot range for x is just x max here. Fantastic, beautiful. Yeah, copy, make a backup. We don't want to lose our code. Paste, run it, run. Beautiful. Slow down, slow down. Fantastic. Okay, I think that's it. Let's play this again. Fantastic, beautiful. They come back to harmony. Hi, Black. So we can now let's look at our version. Dung 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 dung. Okay, so let's speed up. Let's see. And let's play back and forth. Okay, so we are very close. Now something is not still right. You see, just look at the red ball. It's going up and down. It shouldn't go up and down. Okay, it should stay in the same path. But we need to fix it. Okay, but so that's how you do it. Is there anything critical that we are missing of trying to emulate that thing? Is there something critical? Let me think. So path, by the way, you can change the path to any other curve. Then it's gonna be, you see, the path of the balls is this formula. Right now we are using a parabola, but you can change it to like x squared plus minus y, x third power or something, So you're gonna be, it's gonna be like crazy, very interesting effects. That's what these things are. They are just visual effects. They are not actually simulating physics, visual effects. So you need to add some music. Now, about adding music, that can be done by, you see, the trick is to figure out when, for example, when does a sound occur and which sound. So a sound occurs when the red ball hits the boundary on either side. Okay, so when the red ball's x value is near a certain number, like -3 and 3, then you play a sound. Okay, and for each ball, that's the same thing, but each ball have a different sound. Okay, so you need to add that. Yeah, so you can do that, but I don't know how to. I never done this before, but you can do that by just add, like when x is within 3, the value of x, which is this part, the value of this part is near, let's say 3, then you play a sound. Okay, like a quick sound, like 0.1 second of certain frequency. You can play a sound by in Wolfram language, you play a sound by this function. Okay, play, just say play. Okay, play play, let's say sine wave x, x goes from let's say 0 to 9 pi, something like that. Okay, that plays a pure tone. That's too low a tone, so you don't. Wait, 800 hertz. I don't think we can hear it. Maybe so. Let's times 10 something. Wait, times is increasing the volume amplitude, so you need to increase the frequency. See, something like that. Okay, no sound. Well, there's a sound. Can you hear it? But it's too. Let's look at the documentation for play function. So play that function from tmin to tmax. There's a good example here. 400. Okay, 400. Oh yeah, you forgot the pi. So that's a period. The natural period for sine is 2 pi. So let's add that to pi. Okay, so 10 is too low. So you need, for example, they are using 400. 400 is concert A. So that's a key in the middle of a piano, about 5 semitones below. Okay, so stop. Okay, that's the pure tone, concert A. So, but you can, they have lots of interesting sound. So that's a sound wave. Okay, so you can specify how the duration. Where is the duration? Play function, sample rate, play middle A sine wave for 1 second. Oh, this duration is, oh yeah, here actually. Wait, is it yeah, so .1 second, then it's just a beep. Shift enter. Fantastic. Now if we double the frequency, it's the A 1 octave above. Okay. Okay, so if we copy that, then somewhere here we need a condition. Okay, so the graphics. Okay, so here is the graphics. Wait, mismatched paren. What the fuck? Did I fuck up somewhere? Wait, why is my paren not matching? Something is wrong. I think I screwed up somewhere. Okay, so hold on a second. Let me make a copy. Undo, 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 undo. Okay, redo. Actually, just copy that. Paste. Okay, now you need to make a sound. So the sound is here. Okay, now you need to make a sound. So you have to do backup. All you have to do is this graphics part. Yeah, the animation. Actually, we don't need the animation, so the graphics part, you just grab the graphics part. Okay, leave it. So animation, add a semicolon, so that's evaluated dynamically variable here. Then we don't need evaluate anymore. Okay, so for example, double check, go back here, paste. Yeah, fuck. Yeah, what is the problem? Did we have a comma somewhere? Coordinate. Where did we fuck up? It works here. Shift enter. Yeah, the code works there. Copy. Let's not try to so anyway, so that works. So I don't like this format. Okay, let's manually fix it. So graphics animation, so that is our animation. manually fix it. There's one more. Yeah, this tedious. Then there is that. Yeah, so that's graphics. Then you want to also do. So that's animation, and then you want to add a play. Okay, let's just play. Let's play when if x time is greater than x time max minus x max. Okay, so if the time parameter is near the x max boundary, then we play this sound. Okay, play, else no. Okay, else you know, we can remove it. Okay, now we added sound. Let's hope it will work. Paste, evaluate. Yeah. You can, what's new? Manipulate is a list. So what is the problem? Coordinate 3 sides. Something wrong with our coordinates. What? What? Yeah, very annoying. Ah, God. What is our problem? Coordinate 3x times. What is our problem? Check syntax, animation, that. Okay, so you don't need evaluate. Let's redo this. So if x time equals to max, x time max minus x. So if it's greater than, yeah, so this is wrong. So x max minus, so minus 0.2, some small number. Okay, then play the sound, and what else? So plot range. So let's double check everything. So animation, you need declare a variable there. So x time, x max, okay, x max height, y max height, color it, okay, divided by animation red. So animation, you got 3 balls, ball 1, ball 2, ball 3. Then you got 3 lines. I mean, connecting the lines, connecting each ball. So 1, 2, 3, correct. Then axis true and plot range. That's the graphics. That's good. Okay, then you do manipulate. Okay, it should be like that. Then manipulate of 2 things. The first one is the animation we defined. The second one is sound. Okay, so the sound is, so if it's X time, okay, so let's try this again. Hopefully it will be correct. You play, do it. Coordinate 3 sign cell context. Something minor is wrong. Okay, something. Yeah, so let's just clean up this thing. Let's just go full out, make this simpler. Okay, so function 1 equals to, okay, function 1 equals to that. Function 2 equals to that. Let's name ball 1, ball plus 1, ball 1 position. Okay, so ball 2 position 1, 2, 3. Okay, so you got ball 1, you got ball 2, then you got ball 3 position, which is that. Okay, then okay, you got ball 1, ball 2, ball 3. Then you can now simplify all this. Ball 1 position, okay, ball 2 position, ball 3, ball 2. Okay, so then here is the same. So line, now it's so simpler. Okay, you don't need all that complicated. So now it's simpler. It's ball 3, ball 2. Okay, now it's, we needed this. Make it legible. So position now. Okay, so position now, let's just add let's just clean what the, let's make it. Okay, so now yep. Okay, now let's see what errors do you have. So ball 1 position depends on the variables T max, so time is there. Yeah, okay, so don't give me error. Fuck it. No, what I don't know. What if you just remove that? Okay, yeah, you got some kind of coordinate syntax wrong somewhere here. Why is it? Oh, you got ball 0, so that's an error. Ball, y is 0, ball 2, ball 3. Search for ball 1, 2, 3, 1, 2, 3, 1. No, this is 2. Okay. Just copy and paste. It's abuse the system. Yeah, same thing. Okay, so something sine 3 0 cell context x time coordinate sine 0.6 0.8, so this is all wrong. It was working before. X max, y max. So where is y max used? There. Okay, right. So okay, so I don't know why is it. Run that. Okay, ball 1 position. What is the value? Okay, it depends on the x time. That's right. So when x time is manipulated, why is it not working? So somewhere the coordinate is incorrect. So why is it the coordinate incorrect? You know, I'm thinking it's some short syntax error. So this position is incorrect. This should be 2, this should be 3. So they lower, so right? So this should be position 2, this should be 3, okay? Ball position 1, 2, 3. Ball position that's right, ball position 2. Now if you say ball position 2 and replace x time, what? Wait, not max. X time replaced by, let's say x, let's say okay, so that should work. Now if you replace it by 1, you got a coordinate, okay? Now but why so what about if position is ball 1 position? Evaluate, that's good. Now ball 2, ball 3, evaluate, you got a number, okay? Ball 1, 2, 3, you got a number. I mean, you got a coordinate when x time is replaced to a number. So you do have a coordinate, okay? So this is ball 1, ball 2, ball 3. Let's change it. Position. Yeah, let's say just say +1. Let's not rename. Okay, let's just leave it as is. Okay, ball 1, ball 2, ball 3 position. You got that right. And so this whole thing. Oh shit! Wait. So graphics. then you got a line, okay, you got the line of 3 coordinates, 1 2 3, okay, and then the whole thing, wait, how is this work? Did I screw up the, okay, you don't need that, okay, then the graphics, that's right. Okay, so something is incorrect. Something is incorrect. Let's try the animation there. Okay, now remove the semicolon because that suppresses the output. So animation, copy that. If you just run that, you got the problem. And the problem is it keeps telling you the cell. Fuck, what the fuck, what rational? Okay, so what we do is we save this, Control S, save it, close it. Now a new notebook, and we restart from scratch. We evaluate quit kernel. Okay, so quit kernel, quit local kernel. Do you want to quit? Yes. And we restart. Okay, initial. So now we paste this. Let's just double check. Okay, we got the time max. Okay, now time max is yellow. Okay, X max is pink. Yes, X max there. Y max height, that's blue. Y max height, there, that's correct. Y max is a dynamic variable there. And X animation is this. Okay, now the boss comes before the animation. Okay, then the animation. Okay, so we got balls 1 2 3. Are they pairs? Yes. And then we got animation. This seems correct. I don't see anything wrong. Backup, time max. Okay, so copy, paste, run it. Okay, maybe we shouldn't have the that bracket all along. Okay, so remove that brackets in the animation there. Yeah, I don't think it helped. So it's saying so, yeah. Okay, now I'm fairly pissed. We basically did this 10 minutes ago, but now I started to get this kind of error, so somewhere something is wrong. So it says, let's copy that error. So it says, the error message says coordinate that first element and the second element. So we got a rational -1/80. Then we got the cell context time is not a cell context. Okay, this cell context, this is a should be a pair of numbers. Okay, I think I know. Animation next time, so you need evaluate, I think. Yeah, that's probably why. Okay, we removed that and we got all these errors. Fact. we try to be more efficient. We remove the evaluate. Then we got this error, and that cost us like 15 minutes. Fuck. Okay, so you always need to think. You trial and error, you waste time. Okay, if we think about it, we probably know. Anyway, so this code works. Now remember, we need to add the play. Okay, the sound. Okay, let's add a sound now. So make a list of things. Okay, this is how you play sound, and put the animation. So the animation is the first thing. Then if x time is greater than x time max minus a small number, let's say 0.2, then play the sound. Okay, then play the sound, else do nothing. Okay, so now you can just run this part, paste it, run it. Okay, fantastic. Where is the sound? And that's not too fast. Slow down. Okay, so let's try again. If greater than x time max is 20. Okay, so wait, x time max is 20. Oh, not that. Yeah, that's not what you want. You want to x equals to, yeah, so you want to the x width, so there x max. Okay, so when x time, the time parameter is greater than that, then play a sound. Okay, let's try again. Yeah, and this null, I don't want the null, so yeah, so I don't want null. Okay, so nothing represents nothing. Okay, nothing in Wolfram language is like when it's inside the list, and when you nothing, it automatically disappears. Okay, it's kind of a feature you don't see in other languages. Okay, so that will remove the null. Okay, back here, paste, do it. So now you don't see the null. But what about the paren? Shit, you don't want the paren either. Yeah, that's, oh yeah, so it's easy. So you should you just animation, yeah, well, let's worry about it later. Okay, so anyway, so now we should have a sound. Let's try. No. Okay, it play. Yeah, you see, it does that. That's not what we want. You see, you want to actually play it. So how do you actually play it? Well, you need to look at the documentation for play. Okay, so the documentation for play, how do you actually automatically play the sound? Okay, scope sound, audio play. In fact, we can use emit sound. Emit sound emits the sound when evaluated. Okay, let's try. Okay, so that's one thing you can try, and use image sound, or you can try, let's just use image sound. Let's I'm done for today. So emit sound, add that. Okay, copy, paste, run it, expand, play. There it is. Stop. Okay, now the sound should be, why is it playing so long? Should be 0.1 second. Image sound, it should be 0.1 second. Okay. This is phone tone. Okay, so 0.1 second, let's say 0.05 second. Play the damn thing. Okay, I don't know what's going on, but take some time to learn about that. That's it for today. Thank you guys for watching. Bye, guys. If you like my stuff, okay, go to my website, Saudi Talk Show, today's talk show. Let's put the code back. Okay, let's put the code back. Showing browser and syntax correct. There is today's exploration, and we go to the go to my website xali.info, pay me. Okay, xali.info. Go all the way to the bottom, Patreon me, Amazon gift card, and PayPal. Okay, thank you. So we end up doing 2 hours. We actually kind of finished in first hour, but we got thank you, Black Automo. Bye.